For us to look at more complicated examples, we need to start using the Lewis dot structure of carbon to build molecules, as carbon is known to actually bond with itself, making it particularly interesting. So let's get to it. So as I mentioned, carbon likes to bond with itself. That's going to allow us to build bigger molecules. So if we have carbon as a Lewis dot structure, we'll see carbon with 4 different dots around it. So carbon's 4 valence electrons spread out in the Lewis dot structure. Okay, so it turns out that carbon can bond with itself. That's really why we have this class at all. And that's the least important of reasons or things that result when carbon can bond with itself. But it's quite exciting because that allows us to get to things like life, for example. So carbon bonds with itself. Okay, so what that means is if you take a carbon atom and you react it with another carbon atom, you can form a covalent bond. You can have the carbon held together where 2 of the electrons are shared between the 2 carbon atoms. You could, and that would be a single bond, implying that we have a single covalent bond. We could even have a double bond, and in a double bond, we've got 2 electrons from each of the carbon atoms that are shared between the 2 elements. We still have 2 electrons left over that are not participating in bonding, and we can go up to 3 bonds. And this then becomes a triple bond. So the electrons are spread between the 2 elements to give rise to a triple bond. Now, if you look in a single bond, we're going to pick up 1 valence electron from the neighboring atom. So our carbon is now at 5 valence electrons. In the second example with the double bond, we're going to be at 6 electrons. And in the third example with the triple bond, we'll be at 7 valence electrons. Okay, some questions might be coming to mind. What about quadra bonds or something? So carbon doesn't form 4 bonds with itself. Does not form 4 bonds with itself. We stop going from single bond to double bond to triple bond. A question arises then, how do we know how many bonds will be between each carbon? How many bonds will be between the carbon atoms? That's a really good question. And the answer is it depends on what's around or what's available. Okay, let's say, for example, that we've got 2 carbon atoms and 6 hydrogen atoms. What I like to do is I like to always start by just considering a single bond between the 2 carbon atoms. So in this case, we've got 2 carbon atoms and 6 hydrogen atoms. And I should get to this. I should clarify. Let's use this to build a stable molecule. It's a fun exercise. So we've connected the 2 carbon atoms together with 1 bond. That's what I like to do first. So first is connect C's with 1 bond. We'll start with a single bond, not get too ambitious. 2, we see how many atoms are left for bonding. And the answer is 6 times H atoms. And actually, I'll put that question mark. So the answer was 6. We have 6 H dots. And how many open sites are on the C atoms? And it turns out that if we count the number of open sites on the C atoms, we're at 1, 2, 3, 4, 5, 6. I put red underlines underneath those 6 spots, those 6 dots. Now, why do I call those open sites? Open sites are single unbonded electrons. Remember, electrons like to kind of pair up if they can. And so if there's one electron sitting by itself, it's not paired up, it doesn't have a friend, either from the valence electron of the atom itself or a valence electron of another atom that it can form a covalent bond with. So after counting each of these attributes, what we can do is we can connect the available atoms to the available sites. The available atoms to the available sites. And so in this case, what we'll do is we'll just connect hydrogen atoms to each of the open sites. Now, how do I connect a hydrogen atom to a carbon atom? Well, I'm going to draw a covalent bond as shown by 2 dots spread across each of the 2 atoms. A covalent bond or an attachment forms when we take our atoms and connect them by a 2-electron bridge between the atoms. So when we do that, we just look at each of the 6 sites and we add each of the 6 hydrogens to each of those sites, and we've completed the task of connecting the available molecules, available atoms to open sites that are around the carbon atoms. Now we can ask, are we done? To answer that question we would really answer other questions like, did we use all the atoms? Did we use all atoms? And the answer to that question was yes. We had 2 carbons and 6 hydrogens to start, and so we've used all of the atoms that were available to us. The next question we want to ask is, are there open sites left? And hopefully this is no. We have no atoms left and we have no open sites left. If we have open sites left, then we need to start introducing double and triple bonds into our system. Now the last check, and this check is quite important, it turns out, is, do all atoms satisfy the octet rule? Okay, so for all atoms to satisfy the octet rule, we would have to have a combination of 2 electrons around the hydrogen atoms, or 8 electrons around the carbon atoms. Now, if you look and count, each of the carbon atoms does have 8 electrons, each of those 2 carbon atoms, and each of the hydrogen atoms is forming a 2-electron bridge to another carbon atom. So it has 2 electrons matching the electron configuration of helium. So all of the atoms satisfy the octet rule. So did we use all the atoms? Yes. Did we use all the open sites? Yes. That is to say, there are no open sites left. And do all atoms in our proposed molecule satisfy the octet rule? Yes. What we've done is we've built a molecule. We made ethane. Now, I won't redraw it, but ethane is this structure right here. So we made ethane. Good for us. So we started building molecules by introducing carbon atoms. Carbon atoms are so versatile. They're at 4 electrons. They're halfway away from and halfway to 8 electrons. Giving up 4 electrons is a big ask. Taking on 4 electrons is a big ask. So it's just going to result in something that is most likely going to covalently bond with other things. Hydrogen is a really good example. For the most part, we'll see carbon bonding to hydrogen. But what if we introduce other elements like oxygen? So let us introduce an O. Now, what I mean by that is we're going to take our same atoms from before, but also have a neutral oxygen atom in the mix. What I'm really saying is propose a Lewis dot structure of a molecule with the formula C2H6O. So this is our task, C2H6O. In this task I've given you, I've said what I want you to do. Give me a Lewis dot structure. That is all the atoms connected by those little dots that represent their valence electrons. I want you to satisfy the rules using all the atoms, making sure there are no open sites left, and making sure all of the atoms follow the octet rule. So it's the same thing as before, except we have an oxygen atom now. So let's get everything out in front of us. If we have C2H6O, and I would, as you're solving these questions, rewrite that molecular formula. I've been doing this now. This is my 8th time teaching this class in all 7 years. I've seen a lot of people just lose points because they give me a molecule where the molecular formula they're using, C2H6O in this case, doesn't match the molecular formula I gave them. Okay, so let's make sure we rewrite this and we have the players, or the pieces of the puzzle if you want to think about it that way. There are several ways to solve this, and it turns out there are 2 good answers to this question. 2 good answers, and I can show you both of them. But I'm going to show you my general approach to solving this problem. It's going to reduce the number of possible answers you could get. That's not saying the other answers are wrong. I'm just trying to make it easy for us. So if we take this general approach, it seems to work for most cases and doesn't give us kind of bogus elements. So first step is to connect our C atoms. So this is really just an approach. Willoughby's tips, you could say, okay? So this is me just saying, all right, let's start by connecting our C atoms. You don't have to start this way. It's just that if you start this way, I found I tend to get correct answers. Now, for all of these, there are multiple answers, but we don't have to come up with all the answers right away, at least. We just come up with a few, and this is a good way for us to get started. So we're going to connect our C atoms. And I should clarify with single bonds. I don't want to haul off and start drawing double bonds because double and triple bonding, that sort of depends on what we need. Okay, so we have our double and triple bonds. Sorry, let me just check something here. Okay, give you a chance to be caught up. Okay, so 2 carbon atoms that are connected by a single bond. And then in step 2, I'm going to add non-C or H atoms to the carbon open sites. And again, I want to start with single bonds. So I'm going to start with my single bonds. So what I'm saying is we've got our carbon atoms that are now connected to each other. And I've got an oxygen atom, and I usually just stick the oxygen atom down at the end, connecting it by a single bond. Okay? So when I do this, what I need to do is I need to make sure that I'm connecting my oxygens and, for example, my nitrogens and my halogens to carbon atoms only. I don't want to connect oxygens to oxygens because that gets to really unstable molecules, and that's not being, as we'll see at the end of the course, you'll appreciate, those aren't good molecules for us to consider. So if we just stick to a rule of let's connect those non-carbon hydrogen atoms to only carbon atoms, then we can get to more realistic molecules. In this case, we only have one non-carbon hydrogen atom, and that's that one oxygen. I'll connect it. I still have one sort of, I really like the word pair of electrons that comes from the oxygen. Oh, excuse me. I have two pairs. I have drawn oxygen with the electron configuration of nitrogen. Okay, corrected. I have two of these sort of pairs of electrons that can't really participate in bonding because they already have, there's already two electrons, okay, at each of those quadrants around the atom. So I can't put any more atoms around there. But in step 3, what I will do is add H atoms. So I will add H atoms, and the only place I can put H atoms are on these one electron kind of places. So an H atom up here, an H atom up here, H atom, H atom, H atom, H atom. So I've added my 6 hydrogen atoms to spots that only had one electron, and coming with that H atom was one valence electron. So making that connection allows us to form a covalent bond, a 2-electron bridge between each of the elements. And if you look in this case, we actually lucked out. We should check for open sites. Are there any open sites? Our answer is no. If we look, we have no more kind of single electron holes sitting around these atoms. If the answer is no, then we're done. All right, so what we have here is a stable molecule where every element has an octet, even the oxygen atom. Hopefully you recognize the carbon atoms have 4 electrons. Now the oxygen atom has, 8 electrons. The oxygen atom now has 8 electrons, 4 coming from covalent bonds, 4 from electrons that were already in that were already present in its octet, and then all of the hydrogen atoms have 2 electrons. Okay, we didn't have any open sites, so we're done. We checked, we used all the atoms. We matched our molecular formula to Willoughby's original molecular formula of C2H6O. So it looks like we're done with this molecule. It turns out this molecule is a very popular molecule in human society. It's called ethanol, very interesting molecule because it is a toxin. It can kill things very easily, but our bodies are able to metabolize it at least to a point, not after it causes a little bit of delirium and a stupor. Okay, what I want to get into next is I just want to take care of my, I guess, fatigue of drawing so many dots. Kekule structures are far superior to Lewis dot structures when we're talking about complicated molecules. So this is a better way of drawing molecules. A better way of drawing molecules. In Kekule structures, these are really just Lewis dot structures where bonds are drawn as lines. Okay, so what does that mean? Well, if we look at ethane, our molecule that was C2H6 without the oxygen, we had all these dots. And the dots were helpful. The dots show that allow us to see how many electrons are present between the two atoms. But it's always, well, not always. For the most part, the things that we're going to look at are going to have 2 electrons between each of the atoms. So this is Lewis dot. It makes our hands hurt because we draw so many little circles. Let's Kekule this. And by Kekule, I mean I'm going to replace the 2 electron bridges between elements as simple lines. When we replace those electrons as lines, we don't really lose any meaning if we understand what a Kekule structure is. We still know that there are 2 electrons. Each of these lines is really 2 electrons. It's a 2 electron bridge where each of those 2 electrons can count on the valence of each of the atoms that it's bridging between. So the carbon has 2 electrons from that covalent bond. The hydrogen has 2 electrons from the covalent bond. These are things we've talked about. We're just writing it differently because these molecules are getting big. We're only at 2 carbons. Really, we're going to get up to like 20 in many cases in this class. So we need to be able to draw these things faster and more efficiently while still being able to communicate the same information. Whoops, did I finish that page? I did not at all. Okay, let's look at the Kekule structure of ethanol. Okay, in the Kekule structure of ethanol, we originally had something like this. Now there's an important caveat when we're drawing Kekule structures of molecules with more complex elements than carbon and hydrogen. Complex really isn't fair. What I'm saying is, well, let's just look at an example. So that's a little sloppy. Let me clean this up, excuse me. So hydrogen, line to carbon, line to carbon, line to oxygen, line to hydrogen, 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 hydrogen. Okay. What we need to remember when we're drawing Kekule structures is that these pairs of electrons that don't participate in bonding must still be drawn. So we want to draw paired but unshared electrons. So draw those paired and unshared electrons. Those are actually called lone pairs of electrons. Electrons that are paired, and really that means they're in the same orbital, as we will see. Same orbital, but do not form covalent bonds. We can force them to form covalent bonds if we need to, and that's something really interesting for later chemistry, but that's not something we need to worry about right now. But for those of you that maybe have seen it, that's discussing what's called a Lewis acid or base and then a dative bond. Okay, anyway, back to the matter at hand. We have to draw the lone pairs, excuse me. A molecule that we could consider is NH3. This is the nitrogen variant of water, but for it to have an octet instead of NH2, it becomes NH3. That molecule is called ammonia. ammonia has a Kekule structure like this. Okay. I should add that we could have another ethanol Kekule structure. Another ethanol Kekule structure could be one where the lone pairs of electrons, I can use that term now, those paired up electrons that are not shared with another element, paired and unshared, lone pairs can change positions and be in different quadrants around the atom. That doesn't matter, okay? So those lone pair of electrons, they can be the top, bottom, left, right, north, south, east, or west, whatever you want to do, okay? Just as long as they're there, they're drawn when you're considering Kekule structures and Lewis dot structures both, and you don't forget about them. What I want to do, I know this is a longer one, I want to kind of close out with double and triple bonds. You know what? I'll actually hold off on that. We'll do double and triple bonds next lecture.